Okay, so we're looking at transitions with recurrence formulas. So that's when how we can get the next term, and there will be another extra matrix. So all these exam questions are looking at that. So the first one here, it says the matrix Sn plus 1 is determined from the matrix Sn. So this is all just saying we can get the next matrix using this formula. So given this information, the matrix S2 will be. So when you have these recurrence relation ones, so that means when you have that extra matrix, you just have to do it step by step. So because we've got SO and we need to get to S2, we'll have to find S1 first. So into the calculator, so in purple, I'm writing what you will type in your calculator. You're going to do that transition matrix. You're going to times it by SO, and then you'll minus that C matrix. And then what you'll end up with this answer over here, and that ends up being 180 and 130. So this is S1. So therefore, if you're going to find S2, you're going to do the same thing. You do the transition, but you times the one before. So this answer goes down into that formula. So you're going to have S1 in there, and you'll have minus the C again, and you end up with the answer of 148 and 122. So the answer was B. Okay, so this was taken from a question in the exam. It led on from question 3. The school was in a Rocker Stedford competition, okay? So a series of extra rehearsals commenced in April. Each week participants could choose whether they do extra dancing rehearsal or extra singing rehearsals. And the matrix equation used to determine the number of students at these rehearsals is given by. So you can see here we've got a little recurrence situation because there's an extra, well, this is how we're getting the next term by using the one before. So there, using the one before. And we've got also a little extra one. So when you have those extra matrices, you never can use the power trick. So you always have to go step by step. So it says... So let Ln be the column matrix that lists the number of students attending in week N. So the attendance matrix for the first week. So this is L1 is the first week. So calculate the number of attending in week 3. So if L1 is week 1, then we want L3, okay, for week 3. So once again, we're at L1, so to get to L3, we have to go and find L2. So L2, we'll do that by doing that transition they gave us. So we've got that transition. We times it by the one before, which would be L1. So that's this one here. And then we minus that one because it says so to do so in the rule. And what you end up when you do that, so L2 ends up being 180, like that. So now when we go to find L3, we're going to use that same transition matrix here, but we will times the one before, which is that L2. So we're going to use that 180, and we still have to minus that. So you just type all that in on your calculator, and we end up with an answer of this. So this one's actually L3, which we have 168. Now, the top number was dancing and the bottom number was singing, and they just wanted singing. So you would say 68 were singing, extra singing. Okay, so this bottom number was the singing part. Okay, now here when we get these ones, this is where we've got to be we just got to make sure we read it. So of the students attending extra rehearsals in week 3, how many are not expected to return in the extra rehearsal week 4. When we have a normal transition scenario, we never lose any. But when we get this extra bit, and I mean this bit, when you get an extra bit, that's either adding or subtracting people. And because it's a minus matrix, we're actually subtracting those numbers. So in total, we're taking away 5 dancing and 7 singing every week. So you can see, so because we're minusing that, that's how many from week to week. We're taking that away. So if we're going from week 3 to week 4, that's just 1 week. So you can see the total of that is 12. So 12 are not returning, not coming back. Okay, so it was just simply that extra bit. You could simply do it like that. You could have done it by finding the total of L3 and the total of L4, and you would have noticed the difference was 12. You get the same answer. Okay, so with this one, we've got another recurrence. So just make sure, so we're using the term before, and we've got an extra -1 again. And it says we've been given SO, we've given S1, but we haven't been given C. C is missing. And then it says calculate S2. So I can't find, if you think about it, S2 is going to be found by going the transition times the one before, which is S1, but I have to minus this C. Now, I don't have this C. I'm missing that C. So what you need to do is we need to find that matrix C first. Now, what you can do, because I have 2 in a row, I can actually set that equation up and use solve in my calculator. So I've shown you over here. So what I'm doing is I'm going to say solve, and I know what S1 is. So here I write S1. So I write 24.0, 54.3, and 20.7. So that was S1. Now I know I found that by going the transition times the one before, which is SO. So we've got these. I'm not going to write them all out. So we have this one, we have this one, we have this one. We just don't have this C. Now C will have to be like the state matrix. So it's going to be a 3 by 1. So this will be C, and this is the question. So because I know it's going to be a 3 by 1, but I don't know the numbers in it, so all I did is I called them 3 separate letters, and if you type that in and all you just do comma X, Y, and Z, it will tell you. So down over here you can see this was S1, this is the transition, this is S0, and this is the matrix C. I'm going to call it like that. Now, because I did solve and I told, can you tell me what those 3 letters are? And it tells me. So therefore, I know after I've done that, I know matrix C is now 3, -1, and 2. Okay? So I've found that out. So now when I go to find S2 up here, I follow that pattern. So you can see I use the transition times S1 minus C, and then I can find S2, which is that one, which is A. A lot of work in this one. It's one of the last questions. Definitely going to be spending more than 2 minutes on it. Okay, so with this one, a large population of martin birds migrate each year to a remote island and nest and breed. There are 4 nesting sites, A, B, C, and D, and research suggests they move from each nesting site to each nesting site. So we have a transition diagram, and we also have a transition matrix showing that. Now, it said 2,800 and martin birds site at sea in 2008. So we've got 2,800. We might just want to write that as a number, so we're a bit aware of that. In Site C, of these 2,800 martin birds, the number that nest in Site A in 2009. So pretty much we want to go from C to A we want to know what percentage goes from C to A. So we go to C and we follow the arrow to A, and it's 20%. So what we're saying is 20% of that 2,800 will go to A. So when we want a percentage, we change it to a decimal, times 2,800, and we get 560. Okay, question 8. The transition matrix predicts that in the long term. So all you have to do here for this question, you can just put the transition, this is the transition up here, to a high power. Now, because we're talking about long term, which is the steady state. Now, we don't have an initial state matrix, so what I'm going to do, remember how it doesn't matter when you're doing the long term. So I'm going to use 100 because I'm talking about 100% because they just want to say where do they all end up. So when I do that, I notice I get this, and I get 0 and 75, 0 and 25. So what that means, in the long run, 75% end up at B and 25% end up at D. So we could answer that they only are nesting at B and D. All right? So when you don't have a state matrix to use, you can use a percentage. And when you're doing long term, sorry, that should be zeros in there, you can just put in 100 and put zeros everywhere. All right, the last one is a little bit trickier. So it says 6,000 mutton birds are to nest at site B in 2008. And then it said, assume there were equal mutton birds at each site in 2007 and the same transition applies. So the total number of mutton birds on the island in 2007. This becomes a little bit confusing and it's a little bit tricky because you don't know what you're doing. So if we just think about how 2007 and 2008 are linked up. If you were finding 2008 using transition, you would do the transition times 2007. That would be how you find it. So what I'm going to do is so this is how you could find 2008. So if I grab that, I'm just going to grab the transition to save me writing it out. So it'd be the transition times this state matrix. So this will be 2007. Now what they said to me, they said there was equal number of mutton birds at each of the 4 sites in 2007. So I don't know how much there is, but I know it's the same. So what I'm going to do is I'm going to say it's X. So here I'm going to say let X equal number of birds at the site in 07, okay? So, and what that would do, obviously we know when we times that like that, we get 2008. All right, so, and they did tell us something else there. They told us up here, in 2008, there was 6,000 in B. So if you go A, B, C, D, you know this answer was 6,000. So the only way to solve it is to know manual multiplication and how this number comes about. And the way we get that number, because this number is in row 2, column 1, what it was multiplied was row 2 was multiplied with column 1 to give that. So what has happened is you had 0.35 times X, then you would have had plus this 1 times X, plus this 0.15 times X, and plus 0 times X. And all of that, when you did that, it equaled 6,000. So once you have a statement that only has x's and there's an equal, we can use our solve. So you solve and just go comma x, and you'll end up x equals 4,000. So if x equals 4,000, they want the total number. That means I had 4,000 at each of those 4 sites. So what's 4,000 times 4 is 16,000, okay? Okay, question 7. A study of an antelope population in a wildlife park has shown the antelope regularly move, blah, 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 between east, north, and west. Anyway, and we've got this formula or recurrence formula of how to get the next one using that. And so we've been given TD. Now, they gave me A3 and there. And it says the number of antelope at west found in A2. So what we know, A2 is the question. So, that's what we need. We need to know what A2 is. So what you can do is, like what I said before, link up the ones you've got. If you've got A3 and you need A2, find a statement that would link them together. You know that you found A3 by going the transition times A2 and minus D. That's how they found it. So if you look, if you think about it, we have this one, we have this one, we have this one. We don't have that one. So we can type it all up in our calculator, and instead of writing A2, we'll do that 3 by 1 again, and we'll do it the same way. We'll do that X, Y, Z again. So up here you can see I've done that in the calculator. This is A3. So I did solve, open the brackets. This is my transition. Now this is that A2 one I've created. Yeah? And I've just put X, Y, and Z. Here's D. And then we go comma X, Y, Z. So now I know what those letters are. I can now see that A2 would be written out like this. It would be 1630, 2800, and 2270. So that would be east, north, west. And they just wanted the west one, which was 227. So that's probably the easiest way to do it, these ones now. Is just set it up and solve, as long as you can link it up. And then in your unknowns, in your unknowns of your matrix, if there was 4 unknowns, like if it was a 4 by 1, just put, X, Y, Z, and Q or something like that, yeah? Put your extra letter in there. They have to be different letters so that you can see what they are. Okay, so an airline parks all its planes at Sydney or Melbourne Airport overnight. The transition diagram below shows the changes in the location of planes from night to night. Now, there are always M planes at Melbourne Airport, and there are always S planes at Sydney Airport. This little fact there is very important. What that means, what that's telling us is the numbers at each place stays the same. So when that happens, what goes out must come in, yeah? So if some go out, the same amount must come in because they stay the same amount. All right, so that's that, because that was important. Because it says of the planes parked at Melbourne Airport on Tuesday night, 12 had been parked at Sydney on Monday night. So it was Sydney first. If you think you went from Sydney in Monday, and then it went to Melbourne. So they said Sydney to Melbourne, and that was 12. So if we follow the arrow here and we go Sydney to Melbourne was 48%. So we know 48% of the Sydney planes go to Melbourne. So what you're saying is 48% of Sydney equals 12. So if you change that to an equation, it'll be 0.48 times S equals 12. If you're not very good at your algebra, that's okay. Just do solve, comma S, and you'll find out that S equals 25. But they want to know how many planes the whole airline has. So we need to know what Melbourne has. But remember, if we said 12 are going out, that means 12 have to come in. So say that's Sydney, because of this fact here. So if 12 go out, 12 must go in. So what I'm going to say there is, if I go from Melbourne to Sydney, so now I'm saying from Melbourne to Sydney, it's going to be 20% or 0.2, and then that's also 12. So I can say 20% of Melbourne's equals 12. And then if you change that to an equation, and you can do your solve again, comma M, you end up with M equals 60. So in total, there was 60 and 25. So in total, that would be 85. Okay, 10,000 trout eggs, 1,000 baby trout, 800 adult trout were placed in a pond to establish a trout population. Eggs may die, or they may live and become babies. Babies can die, or they can live and become adults, and adults can just die. So from year to year, they change. Here's the transition. Using this information in the transition matrix T, determine the number of eggs in the population that will die in the first year. So what we're thinking about there, we want to go E to D. So if you look for E to D, it's 60%. So 60% of the eggs. So 60% of the eggs in the first year. And they told us, how many eggs did we have? We had 10,000. So 60% of the 10,000 eggs are going to die. So you could do 0.6 times 10,000. So the answer is 6,000 eggs would die. Okay? They want us down here in the part 2 to complete the transition diagram. So you can see we've got the 40 and the 60. So we've already they've done those two numbers, and all the other numbers are missing. So let's go do that. So I've got B to A is 25. So I'd put that. Now, they're putting percentages, sorry, so I'll just put a percentage. I've got B to D. B to D is 75%. I'm missing A to A. A to A, 50%. And A to D, 50%. So that's how your diagram should look. Oops, sorry. Yeah. Okay, the initial state matrix of the trout population is given by there, and they've done that. And it says using the rule, so that's just, you can get the net. This was taken from a little bit older text where they can write it the same way. This is the same as saying your exams would write it like this, yeah? So it's the same, okay? It means the same thing, but so we're going to do it like that. So if we want to find S1, we're just going to do the transition times the one before, and when you do that, you end up with 4,650 and 7150. Okay, and the number of trout predicted in the population after 4 years. So if you want S4, you do the transition to the power of 4 times SO, and you end up with 0.03331.25 and 11 468.75. Okay, so this is E, B, A, and D. Now they just want the adults. So there's the adult. So the number of adult, we'll just say 331. Okay, the transition predicts that in the long term, all of that eggs and baby trout and adult trout will die. How many years will it take for the adult trout to die out? So that is, when will the number of adult trout in the population first be predicted to be 0? So you were already up to 4. You just had to keep going, and you find out that it's 13 years. With this one, what is the largest number of adult trout predicted? You reached the long term, they're all dead by 13. So you had to have a look. Some people would have thought it was at the start, but if you notice SO, you have a certain amount. S1, it drops, but when you come back to S2, you see a larger amount. And so you see S2 when you work that out. So you have to be really careful. You actually see a higher amount in the adults in the second year. And then they die out. So it was actually 13.25. Just a trial and error.
Okay, determine the number of eggs, baby trout, and adult trout that, if added to or removed from the pond each year, will ensure that the number of eggs, baby trout, adult trout in the population remains constant from year to year. So this is probably the important thing. So what they want is the same numbers, so that state matrix to be always going back to the same. So whatever SO is, it needs to be the same when it's S1. So if we have a think about it, so if we did, so whatever SO was, and then if we minus what actually happened in S1, we can see what changes have happened to the state matrix. So if you do that, so SO, there was 10,000 eggs, 1,000 baby, 800 adults, and 0 deaths. And then if you do, so this was SO, and then if you do S1, we end up with 0 eggs, 4,000 babies, 650 adults, and there was 7,500 deaths. So when we subtract them, we end up with, so this matrix in the purple here is telling us what happened. So all 10,000, so there was 10,000 eggs. We didn't have any 10,000 eggs, so there's 10,000 eggs. We lost 3,000, we only have negative 3,000 babies, and 150 adults. So if we wanted, so this is S1. So when we went to there, these are the changes that would have occurred if we wanted to be different to the original. So what we want to do, if we want to do it, to keep it the same as this one, so we would need to add 10,000 eggs, because it's a positive number there. So we will add 10,000 eggs. We will also add here 150 adults, and then because we've got the negative 3,000 babies, we would have to take away, so remove 3,000 babies because we had more babies, so that it would go back to what it began with. So we don't really need to worry about the deaths, because deaths are deaths, and it didn't ask us for that. So you can see when we went from here, because we've got 0 eggs, we'd have to add 10,000 eggs. Here we've got 3,000 more babies, so we need to remove 3,000 babies. And you can see here we've got we've got 150 more less adults, so we're going to add those adult trout, sorry. Okay, the rule SN T minus N. So sorry, this one's a little bit different. All this is, they don't write them like this anymore. We use the SN plus 1 equals the transition times SN. This is another way of writing that, so just pretend that this was written there like that. So that's pretty much saying we can get the next state of trout using the one before. Then they said they need to take breeding into account, assume 50% of the adult trout lay 500 eggs each year. The matrix describing the population after 1 year, S1, is now given by this. So it doesn't matter, we just got this new formula. And so if we need to get the next state matrix, so say we have to here, if we had to get S2, all you have to do is obviously you follow the formula. It says the transition and you use the one before, which would be whatever state 1 is, plus 500. You're just going to times it by this M matrix, which they've obviously given us, and then we times it also by the one before. So there's a bit more work into the calculator, but you just follow the rule. So it says use this new rule to determine S1. So all you're going to do here is just do the chi, which they've given you right here. You're going to times it by this SO. Then you're going to, in your calculator, then you're going to add, press plus, 500 times that matrix M times that matrix SO. Okay, and you end up with, I'll just put this matrix in there like that, you should end up with 200,000 eggs, 4,000 babies, 650 adults, and 7,150 deaths. Okay, so this pattern continues, and then after n years, so this is pretty much what I was saying here, we can just get the next one. So use this formula to determine the eggs after 2 years. So remember, we just found S1 here, which we'll put into that formula. So when we go to find S2, we do the same thing again. So into the calculator, you do this bit, transition times this matrix, this S1, plus 500 times that M1 again, which was given to us, times the S1 again. So this one up here again. And when you do that, we'll end up with 162,500, and then 80,000, 1325, and 130,475. Okay, so use this rule to determine the population after the number of eggs. So the question actually is asking just for the number of eggs, which the eggs is up here, this top one. So we better make sure we write that out. So it'd be 162,500 eggs as our final answer. Need to separate it out. Okay, a market research study of shoppers showed that buying preferences for 3 olive oils, the C, L, and O brand, change from month to month according to this transition matrix. Here's initially what was bought for each of those brands. It says let SN represent the state matrix and the number of shoppers buying each brand after N months. How many of the 8,000 shoppers bought a different brand of olive oil in August 21 went from the brand in July 21? So if we go back to readings, sorry, up here they said this was July, so sometimes it's pretty handy to write underneath that, you know, SO was July. So that means S1 was August. So that would be the next one. So when you think about it, we want to know how many of the Julys all changed. So if we're looking at our transition matrix, if you look at brand C, these guys, there was 5% went to L and 10% went to O. So they would be the ones going to a different brand. So what we are essentially saying is you're going to say 0.05 plus 0.10 of the C in July went to a different brand in August, because it would be the next transition. So we've got to add them. Then if you think about it, if we look at the other brand, so in L, 10% went to C and 10% went to O. So what we're saying there is 0.1 plus 0.1 of the L's in July went to a different brand. And then if I do this last one, O, 0.05 and 0.05 of the O brand went to a different brand, so of O. Okay, so they're all the ones changing. So if I just change that into a sum, what we're seeing is we've got 0, because 5% plus 10%, so we've got 0.15 of the 3,200, because this is of C, so that was C there, plus we're going to say 0.2 times the L brand, which was 2,000. Whoops, I think I missed a little zero there. Plus the last one, which we got 0.5 plus 0.5, so that ends up being 0.10 times the last amount of O brand, which was 2,800. So if you do all that sum, you'll end up with 1,160 changed brand from July to August. Okay, and then it says using the rule, that you can pretty much get the next one using the one before, find S1. So that would be, you just use your transition and you times it by SO. So both given up here. And you just had to fill in the missing numbers. So 1,900 here and 3,040 there. And let's look at this next question. Consider the shoppers who were expected to buy this Carmani olive in August 2000. So they just want the C of the shoppers who buy this. So that, if we look up here, August was S1. So they're just talking about that 3,060. So of those ones, it says what percentage, so remember percentage is always an amount out of the total times 100. So what percentage of these shoppers, so you know the total now, because they said it's of those C brands, so we can say of that. What percentage of these shoppers also bought Carmine olive oil in July 2001? So it's pretty much saying we want to know how many of C to C, and that's from July to August. So if you look at C to C up in your transition, it's 0.85. So 0.85 of the C in July go back to G. So you're really going to say, what you're saying is 0.85 of C in July. So if we change that to a sum, it's 0.85 times C in July, which was 3,200. And that ends up being 2,720. So of those ones, we want a percentage that of the August ones. And then obviously when we're finding percentage times 100, so the answer ends up being 89%. Write down a calculation that shows that O olive brand is bought 50% of these shoppers in the long run. So when they're talking about long run, we know that's steady state. So if we do the transition to a high power times SO, we'll get the steady state. So we'll do that first. and we can see this is what happens. So in the long run. Now they're talking about the brands, and they're talking about this O. Now they're saying write a calculation that shows that the O brand is bought by 50% of the shoppers in the long run. So remember, a percentage is the amount out of the total times 100. So out of all the shoppers, if you add up all the shoppers, there's 8,000. So if we say, all right, 8,000, and they want to know show that the percentage of the O. So if you look there, there's 4,000 of the O, which therefore if you change it by 100, you'll end up with 50%. Okay, so what you needed to probably show here is you had to show first the long run, and then probably just that 4,000 divided by 8,000 is 50%. Okay, further research suggests that shoppers will buy olive oil in the coming months. A rule modelled by this situation. So how we're going to get the next state is we'll use this rule, which means we're going to use the transition times the state before, which would be, they're calling R, plus this B one. So remember, when we use the B, we can't use any power tricks here. So K represents, so we can see the B is missing a number, and they put K there. K represents the extra number of shoppers expected to buy olive oil in each month. R2, if R2 is this, what is the value of K? So what you got to think about is when you are, remember when we don't have an extra added matrix, our numbers remain the same. So this matrix here is adding more numbers. And so more numbers to, our overall shoppers. So if you think about it, when we go from RO to R1, they all shuffle around, but we're adding all of the numbers in B. So if you total that up, it's pretty much 300 plus the K, which we don't know. So here we're adding 300 plus K extra, and that'll get added into R1. And then when we go to R2, we're also adding another 300 because we add that B again, plus another K. So if you look, originally our total at RO, like our total here, the total was 8,000 when you add those numbers up. So that's 8,000. And then after we've added these, done two moving states, so remember we're adding extra. When we add this extra in, we get up to this, which is 9,000. So from 8,000 in there, we added 300, 300, and 2Ks. So if you think about it, we added 600 plus 2Ks to get us from 8,000 to 9,000. So I can say 600 plus 2K equals 1,000, because there's 1,000 more after those two transitions with the two B's being added. So once you get there, you can just use solve if you like, in comma K, and you'll work out that K equals 200.